Hello everyone. In this video we are going to continue our discussion of preparation of alcohols, and here we will be discussing another important reaction, that is oxymercuration demercuration reaction. This reaction is between the alkene and the mercuric acetate in the presence of mixture of water and THF tetrahydrofuran as solvent. Okay, these two guys act as a solvent, and the reaction is between alkene and the mercuric acetate. Mercuric acetate, we can represent it by, this is the mercury that's attached with two acetate groups, like this. Okay, so this first step is called as the oxymercuration reaction, in which this mercury along with one of the acetate groups is induced to the carbon-carbon double bond. In the next step, this mercuriated product is then it is reduced with boron, sodium boron borohydride. This is the reducing agent that we use, very strong reducing agent. Okay, and the product in the reaction is the needed product, that is alcohol, and this step is called as demercuration. So the reaction takes place in two steps. One is oxymercuration and then is demercuration. In demercuration step, the induced mercury is then removed, okay, by a reduction process. So here is a simple example. This is an alkene that reacts with mercuric acetate. Okay, so we have water and THF also as the solvent, and this is the mercuriated product that we get. It cannot be isolated. This is mercuriated product in the first step, and in next step this is reduced with sodium borohydride in the presence of hydroxide ions, and we get alcohol as our product, and the mercury is removed from the reaction. Okay, now looking at the mechanism of the reaction. The mechanism, although completed in many steps, but there are two main steps of the reaction. One is the oxymercuration, okay, and the next will be the demercuration. So in the first step of this oxymercuration, what happens there, when alkene approached to the mercuric acetate, because the the pi bonds or the pi electrons of the C double bond, they are nucleophilic in nature, and this when they approach to the mercuric acetate, they polarize the bond. As a result, there is a small positive charge on the mercury and a small negative charge on oxygen. So when this pi bond attacks the mercury in this step, there is a loss of acetate, one of the acetates. Okay, and we in this step we get the cyclic, this is the cyclic mercurinium ion. This is called as mercurinium ion. Okay, this is cyclic, similar to the, this is similar in structure to the, when we do the bromination of alkenes, there we get bromonium ion. So in the similar way we get here the mercurinium ion. This is a cyclic, okay, cyclic structure, cyclic ion that we get in this case, and we have a small positive charge on these two carbon atoms. Okay, in next step, the water functions as the nucleophile and attacks one of the carbons. Okay, this attack will also be in accordance with the Markovnikov's rule, because if this water attacks this carbon, okay, although there is no carbocation, okay, but stability can be explained in the similar way as we explained for the carbocations, this carbon being more stable as compared to this. So the attack of water, which acts as nucleophile, will be on the more substituted carbon. So we can say that this oxymercuration demercuration reaction, this follows the Markovnikov's rule. Okay, this is followed in accordance with the Markovnikov's rule. There is the attack of water on this mercurinium ion, and as a result, one of the carbon mercury bond is broken. Okay, and obviously this bond will be broken in this case, and in this step, the acetate ions present in the reaction mixture, they now act as base. Okay, they act as base, and they deprotonate they deprotonate this is, we can call this as oxonium ion. This is now oxonium ion. Okay, so acetate, they act as base because they are reactive, they deprotonate the oxonium ion, and we get the alcohol. But in the alcohol, you can see there we have, still we have this mercury, and one of the astates is attached. This is mercurated alcohol still, and we don't want this mercuric acetate, this part of the mercuric acetate, to be in the reaction. Okay, so we can, this actually, this should be color coded with this color. I have just, so this is actually water. This OH is from the water that has been added in this step. Okay, so in the next step we have to remove this entity from the product. Okay, this will be done in the demercuration step. And in this step, what we do, we reduce our product. We are reducing the product by adding the sodium borohydride as the reducing agent. From this sodium borohydride, we actually get H negatives. Okay, hydride, when there is negative charge on hydrogen, it's called as hydride. This hydride attacks on the carbon. Okay, this removes this mercury from the product, mercurated product. And as you can see, the color, the green hydrogen comes from the borohydride. Okay, and OH is from the water that we have added in the oxymercuration step. Okay, and rewriting this product, we can rewrite this product as this, and this is the required alcohol. Okay, so we have to remember that hydrogen, the hydroxyl ion comes from the water that we have added in the oxymercuration step, and the hydrogen, the third hydrogen, which removes the mercury from the reaction product of oxymercuration. Okay, that comes from the borohydride. Okay, now we'll discuss some key points of the reaction. If we look at the overall transformation, is the addition of water across the double bond. Okay, and this is again because we have added the water, so it is this is the hydration. It is again hydration, but it's different, as in the first reaction we had learned about the acid catalyzed hydration. The second reaction, hydroboration reaction, was also a hydration, but the reaction technique was different. And this is also hydration reaction. We are hydrating this double bond, and again this is the alternative method to do so. Okay, and the typical reagents that we use is the mercuric acetate, and in the second step we have sodium borohydride. It's along with hydroxyl ions, and it's along with water. Okay, if we talk about the regioselectivity, so the regioselectivity is predicted by the Markovnikov rule, as we have discussed in the mechanism. Okay, this is in accordance with the Markovnikov's rule, and there is no stereoselectivity in the reaction. See, stereoselectivity is if the reaction product is a product with a particular stereochemistry, then only we say that that there is the stereoselectivity in the reaction. Since in this reaction there is no stereoselectivity, we can get anti-product, we can get syn product. There are both possibilities because there is a rotation of carbon sigma bond, so both products are possible in this case. So this is not stereoselective reaction, means no product with a particular selectivity can be obtained in excess. And the reaction proceeds through the cyclic mercurium ion. These are some of the key points of this reaction that we have to keep in mind. Okay, so we'll continue our discussion of preparation of alcohols in upcoming videos.